In this video, we will solve few interview questions from 12th November post. So let's jump into the first interview question. Refer to below figure. A horizontal force of 100 kN acts at joint E. AD and EC are steel cable. So these are two steel cable member. Let me color using blue color. So this is a steel member. And the question asks, find the tension force in a cable AD. So when, like if we take moment about point B, when the horizontal force is applied, this member, it is going under a tension, and this member going under compression, and cable they cannot take compression, so this member will become not effective. So to calculate the force, let us assume this force a T. We will need perpendicular distance, if we name this perpendicular distance H from point B to line D, and another perpendicular distance from point B, if I name this point as a K, BK is perpendicular to AD. So, and I will name this distance HH dash. So if I take a moment about B equals to 0, 100 into H clockwise minus tension T into H dash equals to 0. So T can be calculated as 100H over H dash. We have been given AB distance as a 9 meter, 60 degree 60, so this will become 60 degree, and so this will also be 60, because total should be 180. So the first step, this distance we can calculate H equals to, this is 3 meter, this is 60 degree, 10 60 equals to H over 3. So H equals to 3 root 3. To calculate H dash, we can use sine and cosine rule. So sine rule says area of a triangle, if we know two sides and the angle between them, we can calculate area equals to half AB sine C. This is sine rule. And what cosine rule says, if I know two sides and the angle between them, then I can calculate the third side C using cosine rule. C square equals to A square plus B square minus 2AB cos C. So using a cosine rule, we can calculate distance AD. Once we know AD and area of a triangle ABD, using sine rule, area of triangle is half AD into height H dash. So once we know area of a triangle and AD, we can calculate H dash. So if we use this procedure, we will get H dash equals to 5.891 meter. And another method is to draw to the scale and with angle we can measure using scale. So we got distance h dash, h equals to 3 root 3, which is 5.196. Putting in this equation 100 into h 5.196 over 5.891, the tension force is 88.2 kilo Newton. Refer to figure 2. 3-span continuous beam. We have 4 cases A, B, C, D. Total length is 3L. Uniformly distributed self weight on all 4 cases. Uniformly distributed self weight. Which span arrangement will have the same approximate magnitude of sagging moment for end span? It means when I load this beam with uniform load, is applied, which span arrangement out of 4 will have the same approximate magnitude of sagging moment for the end span? So here we will get sagging moment for end span and internal span. So which out of 4 will give the sagging moment magnitude approximately equal for all the 3 span? For the selected span arrangement, so the position and location of uniformly distributed live load moment, maximum hogging moment at support, maximum sagging moment for end span and maximum sagging moment for internal span. So how the live load should be placed to get a maximum outcome? So as we remember, like if I have 3 span continuous, then my sagging moment is high for end span. So this case is out. If I remember correctly, when we have a 3 span arrangement, we keep end span, if this is L, we keep end span around 80% to get uniform sagging moment for all the 3 span. So if I check ratio L over 0.8 L, which is, it gives approximately 1 over 0.8, 1.25. So this case is out. We cannot have a longer end span. This case, so let us try this case. Here we have end span 0.925 divided by 1.15, 0.925 divided by 1.15, 0.8. So yes, like the end span is around 80% of internal. So this is the correct arrangement. To have the sagging moment approximately same for all the 3 span. So now we can jump into the second part of the question. How we should arrange live load to get maximum hogging moment at support. So it is a problem of live load pattern. So how we should place a live load? So the answer we have selected, let me make it dark. So to get maximum support negative, the live load should be placed like this: A, B, C, D. So to get maximum hogging moment at support B, this is arrangement. Maximum sagging moment for end span. So for maximum, the live load shall be placed alternate. Maximum sagging moment, so this is a solution for A, B. Maximum sagging moment for the internal span. So the live load should be placed on this only to get maximum sagging moment. Third question, refer to the figure 3 below. Simply supported beam with overhang. We have again 4 cases, A, B, C, D, with different overhang. One is 20% L, second 15%, 10% and 25%. Which arrangement will have a hogging moment equal to sagging moment for the span? So they have asked which arrangement under uniformly distributed load will generate. So here we will have, I am drawing on a tension side. So they have asked which case will generate this moment MA is same as span moment MS. MA magnitude of MA equals to magnitude of MS. So we can start by saying, like, if this is X, moment will be MA half X square W. The load is W into X at a distance X by 2, so it will become this, and MS moment equals to, and if you remember, when we have a precast pile, we lift at 1/5 point, 1/5, so that is 20%. So if we solve this equation, the answer correct will be A, because 1/5 is 0.2 L. Let's jump into the next question. Magnel's diagram for selecting pre-stressing force and eccentricity is a plot of. So when we do pre-stress design, we check two stages. One is transfer and second one service. So if I have a simply supported beam with parabolic profile, when we transfer pre-stress force, at transfer we are generating compression below, tension top. So we have to ensure the tensile stress is not exceeding the acceptable limit, and compression stress also not exceeding not more than the acceptable limit. And during service, after all pre-stress force loss and service load placed we get maybe sometimes tension and compression at the top. So we have 4 equations, 2 at transfer and 2 equations at service. So if we plot these 4 equations, that plot we call Magnel's diagram. So the Magnel diagram we draw with y-axis 1 over p and on x-axis E. So if you remember, the Magnel diagram comes something, this is the safe zone. So if my 1 by p and E falls in this zone, it is so safe. So the answer which we will pick is 1 by p. So always we are drawing 1 by p versus E. So 1 by E we are not drawing, so the answer goes A. Next question. Draw the load path for bowstring under uniformly distributed live load, whole span, mark tension and in a T and compression C. So here we have bowstring girder bridge. So the live load, so the load path, it is getting transferred a tension in the hangers. So the hanger, they are under tension and it travels up and then it travels to the support. So if if you remember, like whenever we have a simply supported girder and uniform load, we have a couple tension compression. So here this member, cord member, it goes under compression and tie under tension. So the members under tension are, these are tension members, and the arch, it's under compression. So for very long span bridges, we go for bowstring. They look aesthetical, and if we have a multiple span, the formwork can be reused. One of a longest bridge in South India for Indian Railway is with bowstring tied arch. Describe through sketch figure hyperstatic stresses in prestress girder. So if a prestress force applied on a simply supported girder, we can have a parabolic profile, straight profile. So girder will deflect and no secondary stresses are getting generated. But if I have a continuous 2-span girder and we have a pre-stressing force. So if we put the load balance method, change in angle, theta 1, theta 2, and the equivalent load balance case will be, we are imparting for upward load So this forces, since it's a continuous structures, this will generate stresses, and the stresses generated due to restraint and pre-stressing force, they are called hyperstatic stresses. So this happens only in case of indeterminate structures. Explain Kern distances and procedure to compute for a given girder cross section. So we use for bridges a box girder, or girder and slab system, so how explain the procedure to calculate Kern distance. So first we calculate moment of inertia. Before we calculate moment of inertia, we calculate CG. So if this is y CG, if the total depth of girder is d, we calculate section modulus, elastic section modulus. So elastic section modulus for bottom, if I write elastic section modulus as S bottom equals to I over YCG, and section modulus top equals to I over D minus YCG. So once I know section modulus, the Kern distance, like top Kern distance, K top equals to S bottom over area, and K bottom equals to S top divided by area. You may be curious to know like why, because the Kern distance is the extreme point where you apply the compressive force, it will not generate any tension top. So if we apply this fundamental equation, P by A minus P into E divided by Z, like here we are using elastic section modulus as S, so just I will write S equals to 0. So for top Kern distance, S bottom divided by area, so the distance K top plus K bottom divided by total depth is called efficiency of the section. Efficiency equals to K top plus K bottom over total depth. So for before we start design, we calculate section properties, center of gravity, moment of inertia, elastic section modulus. Some books they may write this as a Z bottom and Z top, and K top equals to Z bottom over area, and K bottom equals to Z top over area. What are short-term and long-term pre-stress force laws in post-tension members and procedure to compute these losses? So in pre-stress we have two type of losses. The first one, which we call immediate losses, short term, long term. So the short term loss happens First reason, anchor setting. Or it is called wedge set also. Second, which we have due to friction. So we have two effect. One is curvature effect, and the second effect we have due to wobble effect, length. So this curvature and wobble both depend on a type of duct utilized, and the last short term loss, elastic shortening. The member under pre-stress, it gets compressed, so we have loss due to elastic shortening. And in long term, we have three main losses. First, shrinkage of concrete. Sixth, the concrete creeps under sustained load, so creep of concrete. And the high strength steel which we are keeping under sustained tension, it relax, so the loss we call relaxation of steel. So these are the main category of losses: short term, long term. In case of long term, we have shrinkage, creep of concrete, relaxation of steel. And in short term, anchor set, wedge set, the friction loss, one we call curvature effect, and wobble effect, elastic shortening loss. Draw the influence line diagram ILD for 3-span continuous girder bridge. So whenever we have a indeterminate structure, we use Muller-Brusel principle for influence line diagram. So if I have to calculate for influence line diagram, like what we mean by influence line diagram, if I move a unit load over bridge, how like this reaction will change with respect to its position of unit load. So along x-axis we have position of a unit load, and on y-axis we plot the magnitude. So to get reaction at A, we just remove this reaction and we replace it by a unit load 1 kilonewton. And if I draw a deflected shape, that is a influence line diagram for reaction at A. So just remember, if we have suppose if I have to draw for reaction at B influence line diagram, what I have to do? I have to just remove this support, and I have to replace, so all this will remain as a supports, and I will now put 1 kilonewton load. I will check, I will calculate the deflected shape. It would be like this something. So this deflected shape is influence line diagram for reaction at B, and this magnitude, it will be 1 unit, 1 kilonewton. And for shear force we apply 1 kilonewton shear, and for bending moment we apply 1 kilonewton meter moment. So it is asked bending moment at support B, influence line diagram. So if I apply, it will bend like this. So this is influence line diagram for moment at B. So this completes solution for the interview questions asked on 12th November post.